Okay? And every once in a while you guys can see if it moved or something. Okay, so is it possible to cross all these bridges exactly once? Right, and of course I don't want to fly around. I'm in one place in a landmass, I have to go from that landmass, and then I'm in a different landmass, I move to another one, cross a bridge. Can I cross all these bridges exactly once and end up where I started? See, that's how the tourists felt. Hey, that's not a trivial question. Eventually some very famous mathematicians solved it. Yes?
Well, for any landmass with an even number of bridges connecting to another landmass, we consider only two landmasses having an even number of bridges between them, then you can start on one and end up back there. Because you would take one path and then cancel it out with another, and then even number of them you know there are pairs.
Right.
But if in the case of the far left landmass there are an odd number, you're going to have to end up in a place other than where you started.
Right. You mean even if that's not the place I started, because I don't have to start in there, maybe I start somewhere else.
Right. I'm thinking it might be helpful to consider the parity of outgoing.
I think that's true. I think the trick is in the how many bridges are from a landmass.
Since all the landmasses have an odd number of bridges connecting to them, there is a paradox, because if you have an odd number of bridges, if you start outside, I think you have to end inside of that landmass.
I think it's the same argument he makes, that if you're in a
I
landmass, you have an odd number of things. If you start outside, in, out, in, out, in, out, you have to end up in, right? Because it's an odd number of things. So I definitely parity of, is it even or odd, how many bridges we have. It's certainly an issue here, yes?
We could turn the landmasses into nodes and then draw edges between them, and we'll see that there's too many edges.
Nodes and edges as in a graph.
Yes.
Oh, that's great, because that's what we studied today, graphs. Yes, we should draw it as a graph and analyze it as a graph. One of the biggest impact of this problem, it started a field that's called graph theory. Before this problem, there was no graph theory. After this problem, we had a huge field that's graph theory, which enormous impact, not just in mathematics, but everywhere else. So yeah, that's a great idea. Let's draw it as a graph.
Do you have to cross all the bridges?
Yes. And the famous mathematician who solved this problem and invented graph theory, among other many things he invented, is Leonhard Euler from Switzerland. Probably you found the name. You remember this name, Leonhard Euler. This guy invented half of the mathematics at this time. At his time, he doubled the amount of mathematics the world knew. So, I don't like projectors and slides. Some instructors do. I only use projectors and slides when absolutely necessary. I don't know how to draw the city of Königsberg myself. But for the most of this class, if not all of it, we're going to forget about slides and projectors. Okay? So I like that suggestion. Study graphs, right? Here we are, graphs. So let's start with graphs and see where it goes, and maybe by the end of the lecture, we'll be able to answer this question. The lecture, I think, ends at 3:15, so this is a 100 minutes lecture. The recitations are 65 minutes each. I wonder, how can I get more light on the board? You guys know that? How can I get more light? Let's not do that, right? It would be really nice so you guys can see the board better, right? I can see you very well. Is this gonna do something? Or is it gonna do the same? It's such a nice classroom, yet the board is in the dark, right? Okay. Well, so that's what we're gonna start today, graphs. So somebody already said we want to take a graph and see, okay, that's a bunch of nodes, a collection of nodes, sometimes called vertices. And let's say these are like things like A, B, C, D, so on and so forth, or some people call it U, V, W, D, so on and so forth. There's some notation for those nodes. Since we also can find a marker there. And edges. Edges are, you can think of them as connectors between nodes. So how would something like this look like? Here's an example. A, B, C, D, E, F. Those are my nodes in this graph. And I have some connections in between them. So in here, the nodes I have here are A, B, C, D, E, F. And the edges are, I'm going to write it as a pair of nodes. Every edge is a connector. So it's edge, AB is there or not? AB is not there, but AC is there. BC, AD, DE, DF. What else do I have?
EF.
And EF?
Yeah.
So I can quickly check the count to see I got 1, 2, 3, 4, 5, 6, 7. I have 7 here, right? That's the basic definition of a graph. And there's some variations on graphs based on this definition. So one important variation is, or two very important ones, so once we're done with the definition, we can have weights on edges. So an edge, in this case, would not be just a pair of connecting A to B or B to C, will be the connector B to C and the weight on it. For example, I'm going to have weight on the edge BC equals 6. I write here a 6. And I could have other weights, weight on the edge AC, say it's 5. So I'm going to write here a 5 on this edge. And I can put weights on everything. For example, this is a 3, this is a 20, this is another 20, this is a 10, this is 30. So I have now weights on my edges. I could have 0. I could have some weight of something. 0 is possible. And even negative is possible. So can you think of an immediate application or something very natural that have this look like a graph with entities like vertices, and there is edges between vertices, and there's a weight, a natural weight on these edges? Let's give somebody else a chance. Yes?
Like distance between, like if those represented cities and the weight could be a distance.
Right. This is a very visual example, the most natural one. This could be the cities in a county or in a country. This would be the roads between them, and then the number on the road would be the distance between the cities. Right? Very good. So you can see that graphs show up very naturally. In fact, you guys, somebody in the back, pointed out that Königsberg problem is a graph problem even before I mentioned the word graphs, right? So graphs show up very, very naturally in many, many different fields. So we say already, okay, an obvious example of graphs, it's cities plus roads. The Königsberg problem, it's not a road distance problem, it's a connectivity problem. We're going to talk about in a second about paths. That's the Königsberg problem, has to do with how can I go through those paths. What other example of graphs can you immediately, naturally think of? Not the distance graph between cities, but some other graph that, yes?
The price of flights between cities.
Flights between cities. Is that a connectivity type of graph or a distance type of graph? Or which kind? Flights between airports?
Like the price.
I think this example, while it's obviously a graph, the light is even worse, right? It's kind of getting dark. It's not just not enough, but it's getting darker here. Did I do something? Okay. I invite somebody talented to play with those buttons until we find. Seriously, if you want to try to see what we get more light in here, I'm going to put a request for the people managing the building to give us more light. Okay, so flights. I think the flights example is similar to the cities in that it's a very physical, geographical type of thing. I want an example that's not a physical example. Yes.
Social media.
Social media, like Facebook.
Sure, any network where you can follow someone.
So in a Facebook example, what would be the nodes? People. And what would be the edges? Friendships, right? So it's nodes are users plus friendships. Okay. What other example? Again, I want not one that's an analogous to this one, something else. Yes.
Computer networks.
Computer networks. What will be the edges or the nodes in computer networks?
Devices.
Devices are the nodes like routers and hubs and computers, and the edges will be
The wires.
the wires or connectors. If there's wireless, would be the actual link connection that you have with the router, right? So, yes?
Family trees.
What's that?
Family trees.
Family trees. Ancestry. So in there, what would be the nodes?
People.
People. And what would be the edges? Family relations. All right. Quite a few examples. Anybody else? Is there any other obvious graph example?
Circuits.
Circuits. You mean in electrical circuits? Electrical circuits. So I'm not going to say what, but you guys should take a moment at home to say in electrical circuits, what are the nodes? What are the edges? Another example, yes?
Neural networks, such as AI.
Neural networks AI. Neural networks. I think it's nice to leave it as neural networks because if we leave it at that, it's not just AI. Everybody has a neural network in their heads, right? We call it in AI neural networks because we take that neural structure and we do machine learning with it. That's how we predict the next word, or that's how robots answer the phone. So that's great. But there's two different kinds of neural networks. The one that it's in people's minds with neurons, and the one that is built artificially with a computer, right? So we have neurons plus the links or propagations. Any other obvious graph example?
Food web,
What?
like a food web.
The web? Right. I think that's a great example. The World Wide Web. I didn't hear what you say. You said the web or something else?
I was thinking the food web with like predator, prey.
Ah! Let's write that down. So the, how do you call that? There's a name. Food chain? Right. How about the web? The actual web. Who are the nodes?
Sites, websites.
Pages. And which ones are the edges?
Hyperlinks.
Links. Before I move on, I want to make a critical observation about links. There's a major difference between links in the web and roads, typical roads on the street. And that creates another big important variation for our graphs. What's critical about those links that not all graphs have? Yes? One way. One way. That mostly applies to roads. How do we say in a graph one way? There's a way to call the graph that means one way. The answer is correct, one way, but there's a name for it. Directed. So this is a very important variation of graphs. Directed edges have the property that the edge AB is not the same as the edge BA. So you have to be explicit in a directed graph. When you say AB, it's the edge from A to B. And if you want to have the other edge, B to A, you can, but it's not the same. You have to have two edges. So in here, this is undirected. Because when we say BC, we mean both BC and CB. But in a directed graph, BC could be there and CB not be there. Or we can have both. So since I'm here, I know there's a question. I'm gonna get to it in a second. I could say, hey, I want to show you a directed graph. Here's the directed graph. A simple one. A, B, C, D. And now the edges, the way we put the direction on them, we have arrows. So this is a directed graph. Obviously the nodes are A, B, C, D, and the edges are the ones you see. What I want to point out is that the edge AB is there, is part of the graph, but the edge BA is not there. So sometimes edges in a directed sense are represented A to B, and that's what I'm saying, no edge B to A, with a little arrow. And we can define another notion that's important for graph, the notion of path. The sequence of incident edges. Now, if it's directed, in a directed graph, everything with edges have to follow the edge direction. So if it's directed, all problems and all concepts A to B will flow, but B to A will not flow. So in the directed, edges must follow given direction. So in this and here, is there a path from A to D? A path is a sequence of edges that is like in Königsberg, you have to go around. Can I find the path A to D?
Yes.
How?
A, B, C.
That's a path. Right? And we call this a path, right? And we sometimes say A, this is not a straight arrow, it's a curly arrow, A to D. This means D is reachable from A, or there is a path from A to D. How about from D to A? Is there a path from D to A? That's backwards. Yeah, how? D to B to C. Now the concept of paths applies here too. It doesn't have to be directed. If it's undirected, I can have a path, same exact definition, just in here I don't have to worry about edge direction. I can go either way, right? So what's a path from A to F? Can I find the path A to F? I can go A, D, F, or I can go A, D, E, F, or I can go A, C, B, F. You can find multiple paths from A to F. So, yes?
So it says that directed paths must follow a given direction. Let's say in the simplified graph that there was a path from A to B to D. Would that still be
A to?
A to B to D? Like let's say that there was a path between B and B.
Yes.
Would it still be a directed path because then there are two different ways that A could get to D?
Right. You can have multiple paths in a directed. What she's asking, suppose I have this edge. That's what I understood. If I have that edge, how can I go from A to D? I can go A, B, D. Now I can because I have this edge. Or I could go like before, A, B, C, D. So I have two paths between A and D now, right? What I said about follow the edge direction is that all paths must follow the edge in the direction they're drawn. You can't go backwards on an edge. That's not allowed. Yes?
You could go like A, C, D as well.
I could also go A, C, D. True. Hold on, there was a question all the way in the back, or you still?
What about capacity?
What?
What about capacity flow as a graph, right?
The maximum flow? Then in a network sense. Is that what you mean?
Or like weighted graphs, undirected and directed graphs without like graphs with capacity.
You mean the edge capacity?
Yeah.
So I think he's concerned about flow networks. The example is excellent. Flow networks, it's an area of study in computer science. It maps, it models real flow networks like the water flows, water distribution in a city, for example. But it also models other things in algorithms. So flow networks are an important example. It has to do with if I have a graph, how much total water I can send from A everywhere using those edges. Seems a simple problem, but it's not. I'm not sure this is what you have in mind. All right, great example. Yes?
Would it be a valid path A to C to D to B to C to D again? Is
Right.
it a path that repeats?
So I think there is a notion that says simple path. I think it's called simple. Does not repeat vertices. I think that's what he means. Can I step twice on the same vertex or not? Right? Because you're going around. If you can, in a general sense in a path, I think you can. In a simple sense, you cannot. But this brings up another important concept about paths and graphs. What happens if my path steps onto a node twice? So I start from A, da 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 da. I end up in, say, E here or F. And then my path continues and I go in F again. That's the question, right? What must happen in there? So let's do it here. What was the path that you said?
A to C,
Yeah.
to D, to B,
To D again?
to
To B.
D to B,
D to B, yeah.
back to C, back to D.
Back to C, back to D. So this is a valid path, just not simple one. To be clear about that, if those kind of paths are required or not. What I'm asking here is something interesting happened that I by stepping on a node twice, I've created some sort of loop there, right? So if I'm to read this path and I say, here's I step on C, here I step on C again, right? What happened in here? I found some sort of path that's C, D, right? B and C back. This is an important concept for graph that has a name. You have a question or is
I
this?
just had a question, yeah.
So hold on, let me finish this. How do we call this kind of loop?
Cycle.
Cycle. So this is a cycle. C, D, B, C, that's a cycle. Very, very important concept in a graph. It has to do a lot with how easy certain problems are. They are much easier in graphs without cycles than in graphs with cycles. Things like finding minimum paths and representing the graph and finding the minimum traveling distance or something like that. For problems like this are easier if the graph has no cycles. There were a bunch of questions. Let's see. You had a question? No, him.
Yeah, is there a difference between repeat vertices and repeat paths? Or
Edges. Yes, that's not the same thing. You have to be clear what you mean, or the problem has to be clear. Repeat vertices is not the same as repeating edges.
Is there a name for repeating edges? In simple path?
Not sure. There was a different question somewhere in here. Sorry. Still have a question? No. Okay. Yes, question.
Can a node have an edge onto itself?
Yes, but again, those are not simple graphs. Can I have an edge in here? That's what he's asking. We can do anything. Remember, we're in computer science, anything goes, right? But you have to be clear on what's allowed, what's not allowed. These are not simple graphs. When the regular, you just say a graph, typically we assume certain things are not possible. But if we want to have a graph like this, certainly we can. In the web graph, can we have a link from a page to itself?
Yes.
Yes. So that's easy. Right. Was another question? Yes.
Don't you have to step on the same vertex twice if you use the same edge?
If I use the same edge, certainly I have to step on the same vertices twice, yes. But can I step on the same vertices but not use the same edges? That's the Königsberg problem, right? Königsberg problem says use every bridge once. Bridges are what? Edges. Of course, those land masses, we're going to have to step on most of the land masses more than once because there's 7 bridges there and only 4 land masses. But what we want there is to use every edge once, and we can step on the land masses multiple times. Right. Yeah, question? Yes.
In a simple graph, could you have 2 edges between the same nodes?
That's another variation of a graph. That's called a multigraph. That has more than one edge, AB. So we have to find a way to represent that. If we really want to have 3 edges from A to B, we have to somehow know either just the quantity in some problems. We don't need to know to identify the edges by ID, edge 1, edge 2, edge 3, but we need to know there's 3 of them. In some other problems, like the Königsberg problem, do you guys remember, was this case in there? In a Königsberg problem, do I have 2 bridges between the same land masses?
Yes.
Right, so that was a multigraph. In there, perhaps it's not enough to just know the count. We need to know which is bridge A and which one is bridge B, so that when we cross them, we know which ones we crossed and which one didn't. If we only have a count, we say we crossed already a bridge between A and B, but then we're like, okay, which one we crossed and which one we didn't cross. Yes, so that's possible if we call it multigraph. Again, some of this stuff, you want to be very explicit in a problem or a solution. What are you talking about? Is it a multigraph? Can I have edges to itself? Is it directed? Is it not directed? Does it have weights on the edges or not? Everything is possible, but you have to be clear of what you're working on. So a little bit about, I'm going to introduce more notions. I'm going to say a degree of a vertex, number of edges incident in it. So that's again a simple definition. What's the degree of B? How many edges I have connected to B? 2. How about F? F has 3 connections. How about directed? In a directed graph, what's the degree? If I say the degree of C, how do we think about degrees in here? In the directed sense, there's clearly 2 kinds of edges. The edges coming in and the edges going out. So the way people do it is split it into in degree plus out degree. So this is incoming, this is outgoing. And in this case, there's 4 and 2 incoming to outgoing, right? So the way it's drawn here, what's the in degree of D coming in? 3, because it has, now I draw 1 more coming to itself. What's the out degree? 2. If I allow this edge that loops back to D. Most graphs, simple graphs, don't allow multi-edges, don't allow single loops or single cycles, so then in that case we won't have this kind of problem. But you should know what degree is. In a directed graph, degree is 2 kinds, in degree, out degree. In a non-directed or undirected graph, it's just how many edges are incident to a node. So we talk about cycles. Before we move on, let's talk a little bit about representation. Or maybe let's pose a problem here. So here's our first theorem. It's called Handshaking Lemma. This one says the sum of degrees is twice times number of edges.
Could you read that name out loud?
Handshaking Lemma?
Lemma.
Lemma. Lemma is like a small theorem.
Got it. Thank you.
Right? So, is that true? Like, what are the degrees here in this graph? Let's take an example. This is what? 2. So for this graph here, we have what? 2 plus, that's A. B is what? 2 plus C is plus, who's 3? D plus E is plus F is
3.
right? That's the sum of the degrees, and the number of edges is what? How many edges are there? That's what this handshaking lemma is saying, that if you sum up all these degrees, you get twice the number of edges. Is that true? Is it?
And,
Yes.
I would say yes, because for each edge you have 2 connection points.
Very good. He already has a proof for this lemma. I didn't even say something, and boom, we have a proof.
And if you're counting the degrees, which are the points, there's going to be 2 for each edge you create.
So, right, we verified an example. An example is not a proof. Now we want to prove it. And here's an idea for how to do it. Right? Let's establish this, what you said, in a more formal way. You are saying this is a counting problem. Right? What do we actually count? What he was counting there was this, in a visual sense, if you like, that's allowed in computer science. Mathematicians have problems with this, but in computer science, we're good. If we are to mark with a little dot every edge incident to, see, I put a dot here, and in here I have 2 dots, right? We call this incident dots. It's where an edge connects to a vertex. That's what he was counting, those incident dots. So if we look at the vertex X, and it has edges, right? We're gonna count these incident dots. So count incidence of edges into vertices. This number, which is both the left side and the right side, has to do with the total incident dots. That's what this number is. If I am to count all these dots in here, see them? Right? That's going to be, what's that number? 14. So how do we prove this lemma? We're going to do this counting twice. And we know it's the same answer. If we're counting twice, 2 different ways, and we get the same answer, the 2 counters has to be equal, right? That's his proof idea here. It's a counting. So what is counting in here? How do we count the incident dots? So we can say, okay, this count of incident dots, let's just call it C. Some number. We don't know what it is. On the left side, we're going to say C, the total number of incident dots, can be counted, can be obtained by what? In the left side. How do I say yes?
The number of degrees.
Right. I say sum up the degrees. How do I say sum mathematically? Do you guys know that symbol? Right. Sum for every x vertex of what? Degree of x, right? Is that something I need to further explain? Or we take it as granted that this is correct? This count of incident dots can be obtained by looking at each vertex and count the dots for that vertex. And if I go through every single vertex and count the dots, which is the degree, overall, I'm counting all the dots in the picture. Is that true? Okay, hands up, who's with me? This is the first major step and difficulty you're going to have to do in this class. You're going to have to come up with a thought like this, an argument, an explanation, and write it down properly. So there's really 2 things. How do I come up with this? And how do I actually write it down? So I can write it down either like this in English or like this with the mathematics. Both are correct. Again, later on, especially if you go towards mathematics, you're going to be required to write it with mathematics. But for now, we want to write it somehow correct, but also come up with the idea. I want to count all these dots, the incident dots. How am I going to do it? I'm going to go through each vertex and count the dots per vertex and then sum them up. And the dots for a vertex, of course, is the degree, right? The number of dots in a vertex is obviously the degree because every edge incident has a dot. How about the right side? Right side counts the same number, just in a different way. It still obtained the number of dots, the incident dots, just not by the vertex.
Because each edge has 2 points.
Right. So they say, on the right side, I can count these, the incident points, as 2 dots, incident dots, for each what is it? Edge. Right? If you look at it not from the vertex perspective, but we look at this from the edge perspective, every 2 dots that form an edge can be counted as this edge, then that edge, then that edge, then that edge, that edge, that edge, that edge. So that way I can go through all the incident points. I'm counting it 2 per edge. So how do I write this mathematically? If it's 2 per edge, how do I say that? The total. 2 times the number of edges. Now, those two ways of counting, they count the same number. The total, either way, is the total number of incident dots. So the two must be the same. That's the proof. We know that this C is the same C. So therefore, the sum upping up the degrees and count the edges multiplied by 2 should give us the same number. That, I think, the proof that you were having in mind, right? So that's our first proof in a graph. So I have some questions for you between now and Tuesday. Is that true for directed graphs? How would it actually work for directed graphs? Remember, in directed graphs, degrees are a little tricky. It's in degrees and out degree. So your job by Tuesday is to reformulate this lemma and prove it, but not for undirected graphs like I did here, but for directed ones. Yes. There's a question somewhere?
Yeah. I'm just trying. So that handshaking lemma that you did over that example, that's related to that first graph over there, correct?
Right. I was visualizing it on this graph, but the proof is general.
Yeah. But because I was just looking at it, it's that example, that 2 plus 2 plus 2. Plus
Right.
That's
So
the graph.
this is for this graph.
What's the 7th edge?
You're asking how many edges are here? 1,
Oh,
2,
yeah.
3, 4,
I see.
5, 6, 7.
I confused edges with nodes. That's my bad.
That's fine. So I prove it in a simple undirected version. So this is simple undirected. But I'm asking you guys, is it true for directed graphs? Is it true for multigraphs, like where there's multiple edges between two nodes? Is that still true? Is it true for graphs with cycles? So this handshaking lemma, obviously I state it for any graph, but I only prove it for simple undirected graphs. And I'm asking, what about the other graphs? That's something to do for Tuesday, yes?
Okay.
Any reason why you call it handshaking?
It's like, I think every edge is a handshake. It's like you and me, handshake. Yes? No, the idea is totally acceptable. Just writing in English is typically not in the math department, but we allow it in computer science. The formal way is to write it with mathematics. I'm sure you open a math book and you'll see there's some blah, 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 and then a lot of math symbols. In here, if you don't like the math symbols, you can just write in English. Yes?
So for the proof, you're just using like logic to like affirm it rather than going through mathematical examples for every time.
Right, you can do a bunch of examples, undirected, directed, multigraphs, just to figure out how it works. But when you do a proof, it has to be working in general. So I didn't put all the details here of the proof because I want to go through the main intuition. You have to write a little bit more. We say what we want to do as a plan, count C in 2 different ways. And we say here by vertices, and we say here by edges. So I'm counting the same quantity in 2 ways, and I know it's the same quantity, therefore the 2 have to be equal. Yes?
When we talk about the handshaking lemma for directed graphs, do we care about in degree, out degree, or the total?
I don't know. That's a good question. That's your job for Tuesday, right? I said the job is not just to prove it, it's to formulate it correctly. Here's a good point. When I say the sum of degrees, do I mean sum of in degrees, sum of out degrees, all of them, some of them? How does it work? How do you write this handshaking lemma for directed graphs? All right? Yes?
I just want to clarify, in a directed graph, the degree of a vertex is defined as the number of in degrees plus the number of out degrees.
Right. But I'm not sure how this works. Actually, I am. But I'm saying for Tuesday, maybe the whole degree, or maybe just some of the in degrees. That's something that you have to put on paper and figure out. How does it work for directed graphs? All right. I want to add a corollary to this. Where's my paper? So consequence, or corollary of this lemma, which is typically a result that follows straight through from that example. The number of vertices with odd degree is even. I wrote it in English, now I'm going to write it with mathematics. Okay? So I'm going to say the number of vertices x with the property, I'm going to say, let's write it properly. I'm going to say, if you were to look at vertices x, so I'm saying x vertex, with the property that degree of x is odd, this is a collection of vertices, right? In this example, what are the vertices with odd degree? Vertices with degree odd is who? D and F. And now, what this property is saying here is not which ones are the vertices, but the number of them. So you can put the number of them, or you can put the cardinality, which is in the bars. How big is this set? What this is saying, that the vertices that fit in here, they've got to be an even number. So you can check this one in here. It's an even number, right? Because there's two of them, and 2 is even. Again, if you look at the vertices that have odd degree, in our case, D and F, the number of those vertices has to be an even number. And I give you a strong hint already. This is an immediate corollary of this property here. It comes out straight from this. How does that work? Why is this true? Yes. So remember, there's 2 points when you write the proof. Figuring it out for yourself and explain it to somebody else. That's what she's trying to do now. I'm sure she figured it out, but the explanation is a little bit, right? So how do we say this properly? First of all, you have to figure it out, well, how do I get this from this property? But then, how do I write it down? Somebody else, yes.
Oh, sorry.
All right. Somebody else, somebody who didn't, yes.
So if the sum of the degrees is an even number,
Even because it's 2 times something, right?
yeah, you can't have a single odd degree one.
Right, but that doesn't say single. The property does say single. It
You
says,
can't have an odd number of odd degrees.
right, I understand that. And I think I know how you're thinking, but that's exactly restating the property. I still think we need a way to explain that, right? Somebody else, let's see, who else wants to, yes?
Because even plus odd equals odd, so you have to have odd plus odd.
Okay, that's closer than everybody else's mentioned so far, but still not there yet, right? Yes?
If we take what we were talking about in the recitation, where an odd number is like 2n plus 1, and you add 2 of those together, then those ones will add together and create another even number. So
Right.
it becomes 2n plus 2n plus 2.
Right, so odd plus odd is even. We did that in the recitation already, right? And then the problem in here is that while all these small properties are true, the number of vertices in here may not be 2 or 4 or 6. Maybe there's 120 of them. So how do I make that argument for an entire set of degrees? So first of all, let's write down what everybody has in mind without an explanation. I think all of you saw this sum written as, take this property, say we proved it already, and rewrite it for this problem as, instead of writing a sum, I think it would be easier to break it into two sums. It's still the same quantity. Okay? So here's what I'm going to write. I'm going to break it into two sums. Sum from the vertices with degree of x even, sum of those degree, plus I can break a sum into two sums, right? By splitting the x's into the degree that are even, degree that are odd. Is other vertices with the degree of x odd. And I'm going to replace, I don't care about 2 times number of edges like he said very well. All I care about this number is that is an even number. So I'm going to say that's even. Now that doesn't require explanations, it's just coming out straight from this property I just proved. Right? Now I'm looking at this and saying, I need here the degree of x. Right? Now I'm looking at this and say, clearly this problem here is talking about only one of these classes. Right? Which one? The one with the odd degrees. So this second property is not concerned with the first part at all. So now for the first part, we say all these degrees are even, so it's a sum of even numbers. What's a sum of even numbers? No matter how many they are. Even. Is that, remember the 8-year-old neighbor from the recitation? 8-year-old neighbor. Sum of even numbers is even. Would that pass the 8-year-old test? My cousin, my nephew is very smart. He's good at math. How about your nephew? Try that on your nephew. Hey, sum of even numbers, is it even or odd? If you think he passes the 8-year-old, maybe we can say I'm done. I know it's obvious for you that if you sum up even numbers, you get even. Question is it obvious enough to write in the homework, obvious or not? So you got to think about that. So this got to be an even number. We all understand this. But if you have to prove it, maybe you want to actually add an explanation, right? So how do we explain this? That's another homework for Tuesday. And assuming that's even, what happens here is for the result to be even, if this part is even, what about this then? Must be even. Because I have an even plus something gives me even, that something must be even then. Right? So now I'm down to that question. If I sum up a bunch of degrees, all of them are odd numbers. So this is a sum of odds equal even. How many, say a sum with index by I, sum over this index is first vertex, second vertex, third vertex. All of these numbers here are odds numbers because that's what the sum is. It's only the x's that have odd degree. How many odd numbers sum up result in an even number? I know you know the answer, but see, this one requires a proof. I could accept, if I'm in a good mood, that the 8-year-old neighbor agrees with this. Sum of even numbers is even. Maybe, catch me in a good day, I get along with that. But I will never accept this. If you sum up odd numbers to get even, you must have an even number of the stuff you sum up. That one definitely requires a proof. I know it's simple, and it's truly simple, but if you write this down, that's a proof, and you'll lose points. So that one here, by Tuesday, we want a proof. And by the way, in all these proofs, for the ones of you who already know what induction means, we're gonna pretend that we don't know what induction means. So we're not allowed to write the word induction. We're gonna get there in about a month or so, and then everybody gonna write a lot of induction all day and all night. But until then, induction is not allowed. So I can see how those proofs work by induction really well, but I don't want to see induction proofs yet. All right, something that I'm going to do Tuesday in class, or one of you can do it, but definitely think about, that's the main idea of a proof. This is an even number, that's an even number, this might be an even number, that's okay. I know all these numbers I'm summing up are odds. Question is, how many of them do I have to sum up to get even? The answer is an even number. That's what the corollary says here, but we need a proof. So let me keep going with this. Bunch of interesting properties in here that we're going to do next time. Let me show you the representation of graphs. How do I represent in a computer? How do I write the graph? How do I, okay, we draw it on a board and we talked about it, but how do I write it in a computer, this graph? Let's see if I have it here. Yep. I can write it like, so representation. I can do a representation as a matrix, a adjacency matrix. Here's how this works. A, B, C, D, E, F. A, B, C, D, E, F. I'm going to write down on every single A to A to B, A to C, whether there is an edge or not. So I have an edge A to C. I go A, C, I put a 1 here. That means I have an edge. This 1 corresponds to edge AC. And I put a 1, this is an undirected graph, so the edge AC is the same as the edge CA. So I go to C and A, and I put a 1 here. That's the same edge, because that's the same as CA. What other edge I have? I have BC, so where is BC? BC is here, and CB is here. Right? What other edge I have? I have BF. BF, it's here. And FB is here. AD is right here, and DA is right here. And I can have DE, that is here. DE and ED, that is here. EF, that is here. And EF is here. Let's keep something DF, I guess. DF. FD. If I miss something, you can add it in there, but I think I might have gotten all of them. 3, 3, 1, 3, 3, 1. Yeah. Everything else in this matrix that I didn't put a 1 because there's an edge is a 0. So everything else is 0. Adjacency matrix. What we really want to do in a computer, we're gonna want to use something that's called sparse format. Sparsity doesn't change the content of the matrix. It's just a way to write it down so we don't write down the zeros. It's quite useful in a lot of matrices that are majority zeros. This is a matrix that if the graph doesn't have too many edges, it has a lot of zeros. Another very famous matrix that has a lot of zeros, it's what's called a term document matrix. I have a bunch of documents and the words, and I'm counting how many times a word appears in a document. Most words don't appear in most documents, so that matrix has 99% zeros. In terms of memory and usability, matrices like that in computers are usually stored in a sparse format. which is simply saying I'm going to write the values that are not 0, and every other value that is 0 is not written, it's assumed to be 0. So that's something we cannot go into today, but just a warning that if you use matrices like that, typically you want to store them in a sparse format, not full format. The other way to represent the graph is the adjacent lists. That's simply saying if you start from A, here's a list, you can go to C, and you can go to, where else? D, right? Simply writing in a list the neighbors where I can go from A, C and D. And if I go from B, I can go to C and F. And if I go from D, I can go through A and E and F. And you guys can write the other ones. These lists are something you're going to study in the fundis, and most of you have already seen lists. What I'm drawing here, these arrows, those are pointers. So it's the kind of connectivity that you do between linked lists. So these are linkage pointers. The advantage of representing things this way, not in a matrix, first of all, is everybody clear what's written here? For every node, I'm listing the neighbors of that node, and I'm already listing it in a computer science data structure, which is every object here contains the node, where I'm going, and has a pointer to the next object of the list. How many people have seen linked lists before? Most everybody. No problem if you didn't, because you're going to study it in about 2-3 weeks in the fundis. It's just a way to implement a list, which is you need the content of the element and a way to link it to the next part somewhere in the memory, wherever that's written. So typically you have a content and a linkage part of these objects. And that's why we draw it this way. There was a question? Yes?
So why are you drawing arrows like from, like for example in the first row, why is there like a C?
This arrow here?
Yeah.
This is the linkage pointer, I just said that. This is not the edge in the graph. It's saying in a linked list, I could have written this here as in A, C, D.
Yeah.
B conceptually means the same. But how do I represent this in a computer? In a computer, I'll create a linked list. I'll have this object, so it's allocated memory. And every object must contain the content, C or D or whatever, and a linkage to the next object in that list. That's how linked lists are implemented. And again, if you haven't studied that, that's fine. You're going to do it very soon. And actually, there's another linkage at the end that points to at the end of the list. How do I know I'm stopping? Null? Right? Or there is a 0 there that says there is no pointer further. That's the end of the list. Again, no issues if you haven't done linked lists, because you're going to do them very soon. These are the typical two ways to write down a graph. An obvious advantage here is that how many of these objects I have total. If I am to write down all these lists and count not the header but these objects, C, D, C, F, done, how many of these objects total are written there? 14. What each object corresponds to? Why do I have this object here? There is a from. How about this object? There is an edge from A to D. How about this object? An edge from B to F. So every single one of these boxes corresponds to an edge. Right? The reason to have a box, it's because there is an edge from the header to that node. So how many boxes are here? 7 if there are 7 edges, right? The number of edges. But in here, how big is this matrix? This is 6 times 6. How many entries I have in this matrix? much more, right? So this is by default a sparse format. It only writes a box if you have an edge. If you don't have an edge, it doesn't do anything. While this one here creates V times V. How many vertices we have? 6 times 6, 36 cells, and only some of them are edges. Yes?
Wait, why would it be 7 instead of 14?
All right, in an undirected graph, that's a good point. In undirected graph, every edge is written twice, right? There is an edge from A to C, and there is an edge from C to A. Correct. So every edge will be listed twice. In a directed graph, though, it's only going to be the edge once in the direction that's being written. So I don't know if I have this other graph here. In here, what will be the linked list specification? If I go from A, where can I go? B, I'm going to write informally here, B and C. So from B, where can I go? I can go to C and D. And from C, I can go to A, D. And from D, that will be the 4 linked lists that I need in a data structure to map out this graph. All right? I want to point out one more variation. Yes?
Can you do a matrix for direct graph?
Yes, I can. Let's do that. A, B, C, D. A, B, C, D. The only problem with this matrix, as opposed to that matrix, this matrix, how is this called? Symmetric. Every time there is an AB, there is also a BA value because the edge AB is also the edge BA. How about this matrix? Is it going to be symmetric? No. So what is it? A to A, 0. A to B, 1. A to C, 1. A to D, 0. B to A, 0. B to B, 0. B to C, 1. C to A, 1. C to B, 0. C to D,
No, 0, 0, 0.
1 D,
0, 1, 0, 1.
not symmetric. All right. I want to do one more thing here as an important variation of graphs. That we're going to talk about next time. And they call trees. Graph connected. So by connected, what do I mean? I didn't say what connected is, but that's just common English. What's connected? Is this graph here connected? Yes. How about this graph here? Is that connected? No. Obviously not. There's 2 parts and you can't get from here to here. Not connected. Right? Connected is when everything has an edge to everywhere. There's a path from everywhere to everywhere. Not connected when it breaks. Yes?
What about with the directed graph where there's A to B?
That's too complicated for now. Good question. It will take us about 3 years to figure it out. No, I'm just kidding. We'll get to it in the honor section. The regular section will really wait a long time. In there we have the notion of weak connected and strongly connected. And those are very important graph algorithms. So yes, it's a good question. What he asks really, what he wants to ask is what if there's an edge this way, but not the other way? So I can get from this component to here because I have that edge pointing that way. But from here to there, I cannot. Is that connected or not connected? Again, like I said, there is a weak connectivity and a strong connectivity for directed graphs. Let's just worry for undirected graphs where we don't have this problem. This will be connected And without this edge, it will be unconnected. So I have a graph that's connected, undirected, no cycles. That's a tree. Here it is. It's a tree. It's connected, it's undirected, and it has no cycles. No cycles really mean if you start from somewhere, there's no way to follow a bunch of edges and go back there. That's a tree. And I have a question for you for Tuesday. If I have n vertices in a tree, how many edges? I'm going to have a problem that says, here's a tree with 20 vertices. But I don't say who's connected with who. I'm just saying it's a tree. Can you tell me how many edges this tree has? Yes, there was a question?
Yeah. Do you want us to come up with like an answer, or do you want us to prove it?
I always want proofs. So in this class, we're going to have to do proofs. Everything that's not obvious needs to be proved. Okay? So I probably can guess the answer. Anybody can guess the answer here? n-1, right? Can anybody give me a proof? Why is n-1 and not n-3 or 2? Or why does not depend on who's connected to who? That's what we're going to do on Tuesday. Let's see if anybody comes up with a proof. Now for the last 10-15 minutes or so, let's go back to that Königsberg problem. That's correct. So I don't want you to keep guessing. The answer is n-1, but needs proof. And remember what I said about the induction proofs? Not allowed. I know it's very easy to prove it by induction. But that's, by the way, trees are very important in computer science. As data structures. In a lot of problems, we use these graphs, particular graphs which are trees, to create a data structure to map all kinds of things. Not because we need a graph, but we need a tree for an algorithm or for some computation. It's not like we represent our cities and roads with trees, but we need a tree internally as a data structure, like a Fibonacci heap or whatever it is, just to do the computation, which is for a very different problem. Trees are critical computer science data structures. So in particular, binary trees are something that you're going to study right away, I think. So back to Königsberg problem, how does it look? So the problem was, here's a bunch of land masses. Let me see if I can draw rivers here. Right? I'm not very good at drawing. It's a river. These were the rivers, and the bridges were, let me see, there's two bridges here. Two here. One here. One here. And one here. Remember? That was the picture? So what are our land masses? A, B, C, and D. So how do we write this? Somebody says write this as a graph. How do we do it as a graph? A, B, C, So the bridges are the edges between landmasses, correct? So how do I say between A and B I have two bridges, two edges? I'm gonna have to put two edges here. This is a multigraph, right? It's not directed. Don't confuse this with the fact that in some graphs there is an edge this way and the edge the other way. That's not a multigraph. That's just having the edge in that direction and in the opposite direction. This is a multigraph. Because there's two edges between A and B. Where else I have two edges? And then between, where else I have one edge? B to D, C to D, and A to D, right? Again, the bridges are the edges. Hands up who's with me. Good. What was the question, the task? Pass through all bridges once, right? So we need a cycle, because it says pass through all bridges and end up where you started. A cycle that passes through what? How do we say pass all the bridges? What does it mean for my cycle in terms of graph now? All the edges. I should say each edge. Each edge exactly once. Right? That was the condition. You don't want to cross a bridge twice. So the question is there such a cycle? Can you start in some point, go through all the edges? In the multi-edge sense, it means you have to pass this edge and then this edge later on, right? The two edges, you have to pass there twice. I mean, once here, and end up in the same spot. And somebody mentioned an idea that has to do with the degrees, which we just did before, right? For such a thing to exist, what's going to happen with the node? This is a node X. Suppose such a thing exists. So we're going to say, suppose hypothetically. I'm not saying it exists. I'm saying if hypothetically such a cycle that passes through all edges once exists, such cycle exists. By the way, this is called Eulerian cycle. So suppose such a Eulerian cycle exists. What's going to happen with the node? Any node, any A, B, C, D. I have to go into it. I don't want to put an arrow to this edge because I don't want to confuse it with a directed edge in a directed graph. I still have undirected arrows, but in terms of a cycle, I use that edge to either go into X or out of X. Right? Because it's undirected, I can use any edge to go either in or out. Because there's no direction, I can go either way. But because I only pass it once I use it to go in, what? I can't use it to go out. So for every edge that I'm using, which has to be all of them, I have to pass through all edges. From the point of view of a node, right? I'm looking just at one node, say the node A. Suppose such a cycle exists. What's going to happen? You have to go in and then out on some edge, and then the next edge you use in that cycle has to go in and then out. And then the next time I'm coming to this landmass X, I have to go in and then out. And then if there's another edge, that's going to be in. If I want to get out of here, I need another edge. Right? So somebody was mentioned this, I forgot who, that if you, looking at just one node, ignore the rest of the graph, ignore all the landmasses. Say, we're picking this node. What happened here? Well, you have to go in, out, in, out, in, out. If you want to start from outside and end up outside, how many edges you need? An even number. Because for every in, there's an out, in, out. Those things have to alternate. So if you have an odd number of edges, you're going to end up inside if you started outside, or the other way. The only way to end up outside if you started outside, or inside if you started inside, is to have the same number of ins as outs, which at least as a necessity, it's not a guarantee, but it's necessary to have an even number of edges, right? If for any in I have to have an out, or for every out I have to have an in, I have to have an even number of edges. So for this to start outside, suppose I started from here and end up, so in, out, so say this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and this is 8, so I end up here. I need to have an even degree. Again, this is an undirected graph. There's no directed edges here. It's just the way this Eulerian cycle works. It uses an edge only once, and implicitly it says this edge has been used either to go in to this node or to get out of this node, because I can't use it again. So for such a thing to exist, the degree of x has to be even. That will immediately tell you there is no such cycle in here, because what are the degrees? Three, right? So none of them is even, let alone all of them. But I'm going to pose a variation of this problem. Suppose I want a Eulerian thing, passes all bridges once, but I don't require to end up where I started. So instead of cycle, let's call it tour. Eulerian tour. Passes a path, passes all edges exactly once. But there's no requirement to, like in a cycle, you have to get back to where you start. That's not necessary. I can start from B in here, pass all bridges, and end up in D. Is that possible? So in here, we essentially have a theorem that says if you want an Eulerian cycle, all degrees must be even, all of them. And it so happens that our problem has none, not even one even degree. Clearly not possible. But what would be the same kind of characterization? Suppose I want to write this theorem. I want to know when it's possible to have an Eulerian tour, not a cycle. So I'm not requiring leaving and coming back to the same exact point. What do I need? Do I still need all degrees to be even?
You can have two odd ones.
He's saying you still need even degrees, but you can allow to have two odd ones. That's what you're saying? Can I have only one odd?
Yes.
I don't know. How about we decide this? So I can have 0. Obviously 0 allows me to have a Eulerian cycle, or is necessary for a Eulerian cycle. You guys saying I can have 2 odd degrees, but not 1, if you just want a tour, but not a cycle.
So regardless of what you're trying to do, it's possible to have a graph with only one odd degree first.
Okay, because that's from the other theorem we had there, right? The number of odd degrees has to be even. But if I have 2 odd degrees, I can have maybe an Eulerian tour, but not a cycle. Maybe. And now I have a really hard question. What we did here is to prove this one way. If you want an Eulerian cycle, all your nodes have to have even degree. Well, I want to pose this the other way. If all your nodes have an even degree, find an Eulerian cycle. This is not the same problem. This one only says if you don't have all even degrees, you're not going to find an Eulerian cycle no matter how hard to try. Fine. But if I have all even degrees, is it guaranteed to find an Eulerian cycle? Here's an example. this graph? What is the degrees? I'm just going to mark the degrees. 2, 2, 2. Is there an Eulerian cycle here? Can you go around, end up in the same spot where you started, and pass all edges exactly once? Well, is that true for all graphs that have even degrees? If I tell you any random graph has all vertices even degree, is it guaranteed that you can find an area cycle? No induction, please. Remember that. So that's an honors level question. Find an Eulerian cycle in a graph that has all degrees even without induction. I will see you on Tuesday. Let me just stop the camera and Can you guys press the red button? There's either, yeah.